everyone. I hope I'm alive and live and online. Let's just check me whether we are. Yeah, it seems that I'm online. I will just configure my super advanced preview screen on my phone, and yeah, it works, and it looks like it works. Hello everyone. It's super nice to be there and that you are here watching this one of the next episodes about .NET GC internals. As you see, I'm with a little different setup again. Like previously I had a different setup, now I have even more different setup with single monitor, so we will see how it will be working, but I found out how I can overcome that with the laptop, but this will be next week. So say hello, from where you are. As always, it's nice to see that you are from various places. And yeah, the very first question, and I always remember forget to talk about that, so again, today I hope I will just do that. So please do not hesitate to ask any questions. If something is not clear, if something you would like to hear more about, do not hesitate to ask. I will always try to answer. And maybe I will say that it will be covered in one of the next episodes, or maybe it was already covered in one of the previous episodes. So do not hesitate to ask. Okay, and also you can just give me kind of confirmation that you are hearing me and everything is working fine, so I will continue assuming it is. So today, during the previous modules, I was presenting this agenda, which was about what I will be covering in this mini episode series, which is not so mini in the end. And then there was the plan to have generations today being covered. But I thought, okay, generations are super nice, but it would be nice to instead of that, before of covering generations, to cover allocations. So I switched the agenda, and today we will have allocations as a pretty super important part of the GC. And this is, you may be a little bit surprised that it is a responsibility of the GC, which is about the garbage collection, but the garbage collector is in general all about managing memory. So it is just another side of it. On the one side, it is able to reclaim memory, but it needs to cooperate with the whole runtime to allow creation of objects, and this creation of objects needs to be aware how they will be reclaimed, and the whole allocation stuff needs to be aware how the GC is working. So in the end, the allocation, and maybe we can say the allocator, is just a part of the GC. That's why we are covering it here. Obviously, it is also super important from the perspective of the okay, the volume is extremely low. This is not good. Let's just check me why. Audio 111. Check. Let's make a check. How do you hear me now? It should be fine, but it is not, so it is not good. 1 2 3 1 2 3. As always, some problems. So how do you hear me now? We can't hear you well, the volume is extremely low. So give me, yeah, increase the volume. That's interesting because it is like I didn't change anything, but you know. Okay, and now it's better. I just maxed everything I can, and I will put my microphone closer and we will see. And I will try to speak louder, and maybe now it will be okay. Okay, the very first technical problems are behind us, so I hope it will be better. So allocations are part of the GC. That was the thing that I was trying to say, why we were not able to hear me, because they are just as just give me a second, because I hear myself also from YouTube, which is totally doesn't make sense. Okay. Okay, so allocations. Let's move just after all those introductions. So we have two types of allocators, in fact, in the GC, which is just the way how objects may be created, and those allocators are then combined into more complex logic. And okay. And when the very first one, the most important one I would say, is bump pointer allocator. By the way, we will just having 1 hour today again, I hope so, no more, not too much at least. So bump pointer allocator, the first one and the most important one. So the whole idea about the bump pointer allocator is pretty easy. As we can say, nothing is easy in GC, but the idea is like that. You have set of objects that we were just allocating. So we have allocated object A, we have allocated object B and C. So we have 3 objects allocated somehow somewhere, and now we are always tracking where is the position for the next object. That's why it is called next object pointer. Next object pointer, which is also sometimes called NOP in the literature. And so it is just a pointer pointing where we will be creating the next object if someone will ask us for a new object. And then if it will happen, it will be simply moving this pointer by the size of the object that we need. So, in other words, we will be bumping this pointer again and again by the size required from the runtime perspective, for example. So, imagine that we now want to create an object D. It has some size, obviously. So, it will take, I'd say, I don't know, 10 bytes or so, or 16 or something, or bigger, because it is, let's say, 160 bytes. And so we know the size, the runtime knows the size by the metadata. So we are just bumping the pointer, the next object pointer. And now it is simpler, because we know that the beginning of the just allocated object is the previous pointer address. So we know that the object is from here to here. And then we are tracking this next object pointer. So the next object E will be also created here, and we will be simply bumping this pointer again and again. So the idea is pretty easy, which is the most GCs in the world are probably working like that currently. So I will just check the chat, because unfortunately I don't have a good feedback from the phone. Okay, everything is much better. Maybe I'm just saying and talking also more loudly. Okay, so next object pointer, and this is how the things are called in the literature in general about garbage collection. The whole idea is used in the .NET GC. We have only a little different names here. So instead of next object pointer, we have something which is called allocation pointer. It is exactly the same idea. Where is the place for a next object? Then if we are creating object A with some size S, let's say, then we will bump this allocation pointer by the given size, and the object A address will be just the previous address of the allocation pointer. So we have exactly the same idea in .NET. And putting it with one more thing, the question is, and you may wonder, okay, so we are having here this situation that the runtime asked me from the code or from another possible place, someone asked the GC for an object, for a space for an object A. And okay, we have bumped the allocation pointer by a given size S. So the question is now, okay, but what was there before? What we are doing with this place? What we are doing with this memory? And the naive, let's say, the most simple idea is that just after we returned from this allocation procedure, we are zeroing this memory. So it would be two-step procedure. Then bump a pointer by a given amount of bytes and then zero this memory to have a fresh state, because we just need this for safety reasons to return an object to have a space which is zeroed, which doesn't contain the garbage after the previous things and the things that were living there before. So we need to zero this memory before we return from this allocation. But this zeroing is a cost, because obviously we need to fill with zeros a given amount of bytes, which is maybe not so a big overhead if the object is small, but the bigger object, the bigger overhead. And in general, allocations may be pretty often, so pretty frequent, so it would add pretty a lot of overhead if every time that your code is asking for a new object, we would be simply zeroing it at the moment of allocation, because the moment of allocation is the thing that your code is noticing. So imagine that you are newing up an object and your code then needs to wait for this new object. So when you zero a memory at the time of the allocation, your code is suffering from the overhead of zeroing the memory, because we need to do it synchronously. I see some question, so I need to switch to the interesting, still audio problems, but okay, we will see. It's I hope we will manage. Okay, so this zeroing overhead, we need to go, we need to get rid of it to not zero it in a synchronous manner. And because of that, it is also pretty often concept used in various garbage collectors is to pre-zero memory regions. So this pre-zeroed memory region is called allocation context in case of .NET. So instead of zeroing it at the time of allocation, we are pre-zeroing it in advance in some batches. And this pre-zeroed memory region is called allocation context. So now we have two pointers in the end. We have the allocation pointer, which is just the next object pointer, and then we are just keeping information about the allocation limit. So it is the end of the pre-zeroed memory region, and those two constitute something which is called allocation context. Super important concept in the .NET GC. So when you allocate an object, we can, in simple words, say it is being allocated in a pre-zeroed allocation context. And then we will just filling this allocation context with objects that are being created. So we are allocating object by object here, and everyone is happy. We don't have an overhead of zeroing it because it is zeroed, so we will be just filling this memory region with our objects until we will get and hit the end of it, which is just the situation that, okay, so now I imagine I want to create object with this size. I don't have enough space in the allocation context. This is the slow path now happening of allocation. So this was pretty fast from the code perspective. Allocation inside allocation context is super fast because it is just bumping the pointer and returning an address. Everything else, almost everything else, is done because the zeroing has happened before. So if we will be hitting this allocation limit, it means now we need to find a new allocation context. And there is a pretty complex procedure that I will cover later of finding this allocation context. Maybe we need just to extend it with a given amount of bytes, so we may expand it more by another size. And we will just expand it, zero it, and treat it as a new allocation context. And this expanding is happening in non by byte by byte, by in this batches, which is called allocation quantum. So this is the size by which we are expanding allocation context. By default it is something around 8 kilobytes, but it is changing it on the basis of the various heuristics. It may be different, like it will be few kilobytes in size. So we will be expanding allocation context by few kilobytes when it will be filled with objects. And it is tuned mostly to the things like, for example, fragmentation, what will be able to reuse various free space to fit allocation context in, and we will cover that in a moment. So this is a let's say super heart of the bump pointer allocator implementation in case of .NET. So in the end we can say it is super fast because it is just reusing some space that has been zeroed before, and it is just bumping the allocation pointer. So when we look at the result, kind of physical organization, when we look at the whole managed heap, and also again a little bit simplified view, but it may be visualized like that. So we will be having our objects and we will be allocating somewhere at the end within the allocation context, and then we will grow our allocation context or maybe find another place for an allocation context. All this is happening inside the committed memory, and also we reserve a lot of memory in advance. I will cover this reserving, committing, and overall segment concept as a physical organization of the managed heap. I will cover that next week when I will be covering generations, but we can imagine that I need to introduce a little bit of it now because I will be just showing something more in the context of allocations, but it is something like that. We are in an ideal situation, let's say we are allocating at the end of objects by or inside an pre-zeroed allocation context simply. Again, I need to check the chat because it is, I don't trust my preview on mobile phone. Okay, it looks like there are no questions. So then we said allocation context is nice because it is super fast. We can return the pointer and just check whether we fit within the limit, and that's all. Then we could create kind of dummy or naive bump pointer allocation, but obviously it needs consider somehow the fragmentation. So after some time you can imagine that we have allocated our objects, they were gathering here at this memory region, and obviously sometimes the GC may kick in and we'll notice that some parts of those or some groups of those objects are no longer needed. They are not reachable, so the sweeping GC probably may kick in, and it will create those gaps for with the free space. We know that they are called gaps, and that there is a list that keeps a list of all those free space to be somehow used. And in this particular scenario, it is just unused free space because we don't know how to consume this knowledge. And to overcome the problem of this fragmentation, in the naive implementation, we could simply compact the managed heap from time to time to get rid of those free space gaps, and obviously then the allocation context could be pushed back at the end of it. So it will be something pretty easy to understand. So we are just allocating our objects, allocation context by allocation context. After some time, some parts of it, those objects are no longer needed. We are creating the free space. Objects are again and again constantly created at the right in the allocation context, and when we notice that the fragmentation is big, we can say, okay, so it's now time to compact, get rid of the unused free space, and start again the whole story. So we have again allocation context, and we will be allocating object by object to the right. And it could work, but the problem is here that we don't reuse this free space in this naive dummy implementation. So it is something that, okay, we could just don't care about them, those free spaces, because we are not doing anything with that. And this is not how the .NET GC is working internally, because it is really interested in reusing this unused free space, like to make it used free space. And how we can do that? We can do that simply by allowing the allocation context to fit within one of those gaps. So if the gaps is big enough, it is like few kilobytes of empty space, and when we fill one allocation context, the GC is able to look around inside those free list items and find a gap big enough to fit it with a new allocation context. So it will be consuming our fragmentation for its purposes and consuming it for the allocation context simply. And this is super nice, because without compacting, we are fighting with the fragmentation. We are not even fighting with it. We can say that we are reusing, making use of the fragmentation. Without the whole overhead of the compacting, we can reuse it even if we are only sweeping. So our allocation context will jump inside our gaps. This is super nice, and now the memory will be filled, because obviously now the allocation context will consume this memory. We will zero it, and everyone is now happy. If we will allocate an object, we will be just filling this gap. After that, maybe this gap will be reused as an allocation context, so we will fit this memory region, and so on and so on. So in the end, we will consume probably most of the free space inside this particular memory region. Maybe it will be not using all the space. Some gaps may be not big enough to use it as an allocation context, and they will count as an unused unfortunately unused free space, and then this will count into the overall fragmentation, the unused fragmentation, and it will be one of the main reasons to decide on compacting, if those gaps will be problematic enough that, okay, unfortunately we cannot reuse them, so we need to compact. But the whole idea is to reuse and make use of fragmentation. If you have any questions, do not hesitate to ask. I will check how the things are going on the chat. Okay, it is all fine, I hope. So let's just take me a So this is a smart bump pointer allocator that reuses free space, and we will return to that when talking about the free space. One more thing is, you can imagine, okay, so maybe on this slide, imagine that, and you don't have to imagine that because probably it happens super often, you have multiple threads in your application. So for example, we are processing multiple HTTP requests or anything else, and every such a thread may allocate, obviously. So now there we have a problem, because if various threads are trying to allocate an object, they would try to reuse the same allocation context. So one thread number 1, could try to fit and create an object inside the allocation context, then another thread also would be interested in allocating and so on and so on. Many threads may try to access this memory region at the same time to allocate something, which means probably it is not trivial from multi-threading access perspective. We obviously could overcome that by creating a huge log, like a huge, I saying because every log is pretty atomic bomb way of solving problems in multi-threading, but it could be the single log that just synchronize access to this memory region, and every thread is then waiting if any other thread is also trying to allocate at the same time. But allocations are super common, and they needs to be really efficient, so adding any such kind of synchronization overhead would be just an overhead, and we don't want to have any overhead. So this naive implementation using any kind of log to access allocation context is just not efficient. Obviously we could think about any kind of log-free way of programming, which is trying to be more efficient way of accessing the same memory region, but there are also caveats. They always paths, the slow, unhappy paths, even in such approaches. So in the end, to get rid of all this synchronization overhead, unfortunate overhead, we can do another thing, and we can think about it as a super simple but really efficient solution. Let's make that every thread has its own allocation context, and this is a super easy solution. So if you have 3 threads in your application, they will be having their own allocation contexts, and that's all. That's the simple solution, because now we don't need to have any synchronization between them, because every such a thread is using their own separate memory region, and no synchronization is needed. So in the end, we can say that we will have as many allocation contexts as number of threads in your application. Manage threads. So yeah, every time you create a thread, the allocation context at some point will be created for it, as if it will start to allocate, and probably we can expect it will, because it's hard to imagine to have a managed thread that does not allocate anything. So this is an overhead that we will have, but it allows us to really efficiently implement this bump pointer technique. Every thread, when allocating, will be just simply interested in its own memory region. It will be tracking its own allocation pointer and its own allocation limit. That's super nice. Okay. Okay. So in the end, it may look like that. Some allocation context will be inside gaps because the gaps are being reused. Some allocation context will be at the end because it is where the kind of default solution when the allocation context may be created. When you create a new thread, a new allocation context will be created. When the thread is dying, then the allocation context will eventually die also, and so on. Question, I see some question. How to avoid lock when struggling? And now I need to check whether you see the question on the, yes. How to avoid lock when a thread gets its new allocation context? How to avoid lock, Christoph, when a thread gets its new allocation context? I don't see why it would be interesting, why we would like to have any lock when getting new allocation context. You are referring to the moment that you are finding new allocation context, right? So then you can simply create at the end of the space, because if you would like to reuse free space when the new allocation context is created, then you probably need to access the free list in a synchronized manner, but you can, for example, in an efficient way create it at the end, and then you don't need this synchronization. I hope it answers your question. And another one, will it not increase the fragmentation? No. Like in general, this is implemented that in that manner to not increase the fragmentation, so my immediate answer is no. But if you could elaborate what in your opinion might increase the fragmentation, I will try to answer in more details to show that it shouldn't. I hope so. I will be able to prove that. So if you can rephrase the question, and I will just continue. So yes, this is how it is working in the GC in the general. If looking at the high level view of the GC in .NET, you can imagine it like that. You have this managed heap which is constantly garbage collected. Some gaps are created that we could call free items. They are consumed for allocation contexts, so we are just consuming the fragmentation and make use of it. And after some time, unfortunately, we will notice that there are so many small gaps that we are not able to use them as allocation context. So there will be decision to compact, because this fragmentation will be severe enough and problematic enough that we need to compact. So the compacting makes sense from time to time to get rid of all this mess in the free space, but sweeping from this perspective is pretty good because we can reuse this fragmentation. Okay, I see on the chat some discussion. The question is, do we have like two allocation contexts for a thread, one for large object heap, one for small object heap, and for pinned object heap? I will cover that. In the end, there is only one allocation context per thread, and I will cover that why it is like that. Yes, this is kind of overhead, or kind of compromise that and trade-off that we need constantly to consider whether it is just good enough to consume the end of the space, of just add a little of overhead and consume the FreeList item. And the FreeList item searching, which will be covered in few minutes, is pretty efficient, so this log is not so big. And I will try to recall, but as far as I remember, in a regular allocation, this FreeList item may be consumed. So yes, there will be some overhead from time to time when the allocation context is filled, but it is not huge because it is like few kilobytes of allocations. So we can live with that. I would say that there is an unfortunate trade-off here that we needs to live with. Okay. I don't see the Amit. Okay, so Amit, probably you have that in mind also. That is Chris talking about now. So yes, this FreeList is used also during allocation. Not that it is like always created at the end, because that would introduce fragmentation for sure. Maybe I said that not clear enough. Okay, so we have this situation. This is pretty nice overview of how the things are happening inside the GC and how the sweeping and compacting GC cooperates with allocations. Sometimes if it will be just not having enough memory, we will commit more from the operating system. Sometimes we will commit from the reserved memory. Sometimes even we will try to reserve more memory if it will be just not enough. But yes, this is the overall picture that describes the GC internal workings pretty nicely. So let's now move to the FreeList allocator. The bump pointer allocator has been covered a little, and the FreeList allocator is the second one, which is cooperating with the previous one, as you already seen. So we need to search through a free item list, because we have something like the free item list. We have covered that previously. So as we know, it is just living on the managed heap as a set of the single list items of free space. So it is something like the every item in the free list item points to the next item. And now the question how it is implemented, how we are searching through the free list items. And obviously you can think about few algorithms, like we can find the best fit. So we would need to traverse all the free list items, because what is the fit here? We are in a need for we having these gaps in the free list item. We have these free item elements, and we need to find a place for a Go object for an allocation context with a given size, like let's say it is something like this size. And now we could, if we would like to find the best fit, we need to traverse the whole list and find the gap which is bigger than this size, but with the smallest, the closest to the size that we are finding. So it will be probably this element. So we would need to traverse all the elements, find that okay, we have the 4 elements, there is nothing more here, so this is the best fit. But obviously the finding the smallest block fitting is problematic, because we need to traverse linearly the whole free list item, which is an overhead again, and we are always trying to avoid an overheads. If we would use it, we will consume part of it, so we will just kind of make, for example, this part and use it as allocation context, and this part will be put again into the list. So this part is called leftover, kind of, because it is just the part that has been not consumed from this gap, and it fits again inside the free list item. So the leftovers will be the smallest possible with the best fit, but the overhead of finding it is pretty big, the linear scan of everything. Then we could imagine that we are not finding it in best fit, but the first fit. So the first fit is the second approach. So we are traversing the list and trying to find the first block that is just big enough that will fit our allocation context, which is faster because it doesn't require scanning the whole list, but unfortunately it is pretty inefficient in terms of using the gaps, obviously, because we will just use, for example, this one, and then we will just leave this big leftover that we will use this part for our allocation context, and we will leave this leftover inside a free list, so we will be consuming this inefficiently. So this both approaches doesn't sound like a good approach, and in the end this is not what the .NET is doing, because it is just doing that with the help of buckets. So we have just buckets that will combine the idea of first fit, that will just be the first fit inside a bucket of various size ranges. So we will be just keeping a list of various lists. So our list in the end will be splitted in various sublists with the sizes of gaps of with the given ranges. And this is how it is organized in the end. So we have this free list, which, as we know, it is partially stored on the managed heap. Those gaps are stored there. There's this element to the next element, the pointer to the next element. the size of it. And just to recall how it is organized, I was showing that during the plan phase. This every such a gap on the managed heap is looking like that. We have it in the end is very similar to a regular object. So the method table pointer is there, and it is pointing to a special free object method table, a hard-coded free object method table saying, okay, this is a gap, this is a free object. And you will see various tools showing that, including WinDBG, for example, as a free object. It is just able to understand that this particular method table pointer is a free object. Then we are keeping the size of it, which is very similar how arrays are stored. So the first field inside it is just the size in terms of bytes in this case. So it is treated as kind of byte array with a given size. Obviously we don't care what's there because it is just a free space to be reused. So we don't care what's there after this. But then we have the pointer to the next free object. So we are creating this as this linked single list link. And then one more thing at the object header. We are keeping here a magic which is called undo, and I will describe this undo soon, very soon. So this is how this free space is organized, and it is again a single linked list which is organized into buckets as I described. So in the end we will having various single linked lists of various sizes. And allocator will be just our top level entry point for all this information, let's say metadata about free space, and then will be just given number of buckets depending on the generation. Every such a pointer here will be just pointing at the description of our free item list, and there will be a head of this being stored, and for the efficient purposes also a tail, but the head will be pointing to the first element inside our bucket, and then for example, if it is just not a single element, but there are multiple elements in our bucket, they will be linked by our next element pointer. Some buckets may be empty if we don't have gaps of a given range in size. Some may be pretty big because maybe we are having multiple gaps with a given size range, but it really depends. And now so we have those buckets, and this is pretty efficient now. So for example, if we are interested in finding gap of 100 bytes, we will calculate in which bucket this size fits in, and we'll start to traverse this from the beginning in the first fit manner. First fit is efficient because we will pretty fast able to find it, but leftover will be not so big because we are just considering a bucket with a specific range of sizes. So it is kind of trade-off between the size of how good we are fitting in terms of size and how fast we are finding something. And as you see, various generations have different buckets, and I didn't say a lot about generations yet. We will cover generations next week, but it was mentioned at least once or two. Managed heap is split in generations, as you probably know. We have 3, 4 or 5, depending how you count, generations in .NET. And as you see here, there are various in terms how buckets are organized. So for example, generation 0, because we assume that it is not so big, it has only a single bucket. So it is indeed real flat single linked list of items of free space. And the bucket size is, the first one is maximum, like obviously it is fitting all the possible sizes. The same for generation 1. So those two small ephemeral, so-called ephemeral generations, are simply kept as a flat list of elements. Generation 2, which is much more often interested in fighting with fragmentation and much less compacted, because this generation 0 and 1 in the end is pretty often compacted, so we don't care about reusing this free space so much. But generation 2 and large object heap are very rarely compacted, so then we would like to have a lot of the free space to be able to reuse. Then we have, for example, 12 buckets, and the first bucket size is depending on the bitness of the runtime 256 bytes. The next one will be 512 bytes, and it will be just doubled bucket by bucket and so on. So we will have 12 buckets inside our metadata about FreeList, free space. So for example, in generation 2 we will have buckets of these sizes, and I will try to not list all of them because it doesn't make sense to waste time for that. But now, for example, if we will be interested in finding free space in generation 2, which is 2 kilobytes or 1.5, we will fit inside, we will look at this bucket, and this bucket contains free space which is between 1 kilobyte and 2 kilobytes, and so on and so on. So it will be, we will be consuming one of the free space from a list maintained by this particular bucket. Okay, if you have any questions, do not hesitate to ask, as always. And then one more thing is that this Gen 0 and 1 list is pretty flat because it contains only of a single bucket, and as you even see, free items are then really fast being discarded. So if we ask for a given size, and if we traverse this list and a given free space doesn't fit, we are discarding it immediately, and we are treating it as an unusable fragmentation. So it is pretty dynamic. We don't want to have a huge overhead of maintaining FreeList in Gen 0 and 1. One of the reasons is that we would like to really fastly answer and find a free space there, and this is all again about synchronization overhead that we were discussing before. So if it is really dynamic, doesn't contain a lot of elements, we are discarding elements from there pretty fast, and if an element was just not big enough, we are saying, okay, so let's treat it as unusable fragmentation. It will pretty often trigger compaction, because it may trigger compaction because it is much more likely that we will be creating a fragmentation there. This is like another trade-off between the speed, overheads, reusing fragmentation, allowing the overhead of the compaction, and so on and so on. And large object heap also, it is like that. It is from the first bucket size is of a given size, 64 kilobytes, and then there are 7 buckets of bigger and bigger free space items. You may be surprised that then we are maintaining FreeList allocation and FreeList in general for all generations, because you may remember from various articles that you can allocate something in Gen 0 or large object heap. So why we need maintaining the FreeList allocator for generation 2, for example, if we don't allow to allocate things there? We will answer that next week. In general, this is that this whole allocator idea is reused both for allocating things like we are describing today, allocating objects, but also it is used internally by the GC when the compacting is happening, it is trying to reuse a fragmentation from the upper generations, and then the whole idea is again the same. It is trying to find the place for a plug in an older generation to promote it there. So that's why we need FreeList allocators for all generations. We will return to that next week. This undo thing is about planning. If you remember, the planning is to calculate something that will be used both for compacting and for sweeping, and then we decide whether we will compact or sweep, and based on the all knowledge that we calculated during the plan phase, we are compacting or sweeping. Then only thing here is that sometimes the only place, as far as I remember, when the information about compacting and sweeping is overlapping is in this field when you are planning to use free space. So because the plan phase is doing exactly that, it is threading these free space items, it may be if it is promoting objects between generations, it may decide, the planning phase may decide to use a particular element of the free space for objects that are promoted from the younger generations. And then it will, for example, decide that, okay, during our compacting and promoting things, we may decide to move objects here, and we would like to unlink this element from the free space. So this free space item element needs to be taken out from the FreeList allocator because it will be planned to be used for objects. And okay, that's fine, we can do that. We can unlink this element from the FreeList allocator. But then what if in the end, after the planning phase, it will be decided not to compact but simply to sweep? We have lost the information about this free space because the plan phase has calculated what if we will be using and doing with this free space if compacting will happen. And if we decide not to compact, then we need to revert this decision, and then we need simply to link this item again inside our free list, and that's why we are keeping this undo pointer. This is exactly for that. If sweeping has been decided, we simply revert this unlinking item operation to revert typical unlink operation on a single link list element. So we are just saying because we stored what the undo is storing in the end, it is storing the pointer to this element that we just unlinked. So we know that the previous free space element has this pointer, and if we want to revert back this operation, we can just take this pointer from there. So let's call this pointer P, and because we have stored this pointer, we can thread things again. So now we can just say, okay, so I'm just putting this pointer here, and this pointer 1 I'm putting here, and the pointer 2, which is here, I'm putting here, and because of that the result is as previous. So now I have threaded again this element inside our FreeList item list FreeList allocator. So this is just for that, for reverting the unlink operation during the plan phase. I hope you see that it makes sense. If not, I can try to explain it again. So that's why we need this undo, and it is kept inside the object header because we don't care about the object header because it is just our free space, so we are not using the object header for anything. Okay, let's check the chat if you have any questions. If you are there, okay, you are some of you are still there, and no questions at least now. So having covered those two ways of allocating, let's look what's happening when you are really allocating an object. So in your code you are newing up some type, let's assume now that it is just a reference type, which is not a value type like struct, which is a little bit different story, because probably you know this struct could be allocated on the stack or maybe even registered to the CPU registers. So assume that it is really a class, a reference type, so we are newing up it in your code. This C# code becomes new object IL instruction, and then this new object is just interpreted, obviously interpreted. When the JIT is emitting code on the basics of this code, it is seeing new object IL instruction, and it is then doing magic that will be just emitting code that will be responsible for allocating this particular instance of this type instance. And it gets pretty complicated. Yes, I mean the undo thing is pretty complicated. I hope that the things that I will just show you now, that will be just reusing the concept I have just described, will be a little bit simpler, because they are a little bit more high level. So two questions. If the JIT, if you have this new object IL instructions, two questions might be interesting. First of all, who resets object fields to defaults? I hope you know already that it is happening because we assume that we are operating on pre-zeroed memory region, because we are inside an allocation context, and because of that the objects fields are set to defaults, which is just interpreting 0 as memory. Integers will be 0, references will be nulls, which also again means 0, doubles will be 0, and everything will be 0. So all the fields will be set to default because we are allocating inside allocation context, pre-zeroed memory region. So this has been covered. Also, who decides where to allocate, whether it should be small object heap, large object heap. Now we have pinned object heap. So who decides about that? And the answer is the JIT decision. So obviously it needs to be JIT, because we have this new object IL instruction, which while JITting we need to make something. We need to emit code for this new object IL instruction, and the JIT is now in power to decide what code should be emitted for this particular new object IL instruction. And there is this get new helper static method. You can look for that for this in the course here, in the runtime repository. This is the method that is in the end called by the JIT to decide what routine, what method should be used for the code emitted for this particular new object IL instruction. So inside this code, which is executed during the JITting of the method, there are some checks. For example, there is this check whether the size is bigger than large object size, or if it has finalizers. If it is true, it will emit code which is called the JIT new, and we treat it as a slow path. This JIT new is written in C++ inside the runtime, and it is in the GC code. And because of that, we are treating that as a kind of slow path. So if the size is bigger than large object size, which means we would like to allocate this object on large object heap, then we will use this JIT new routine. The same story for pinned object heap now, which has been recently added. Or if it has finalizer, also we will use and emit this slow path method that later on will be called when eventually the emitted code will be executed. If both conditions are false, we are then checking various conditions and emitting one of the assembly code routines. On Windows, on non-Windows like on Mac or Linux, there is this JIT new S multi-process as I don't know what this MP in fact means, fast portable routine being used. On Windows, there are additional checks, for example, whether we are using allocation context, which means whether we are, for example, using server GC. If we are using allocation context, then this routine is being used. If we are not using it, and sometimes it happens, so for example, on a single logical processor machines, which is pretty rarely currently, there will be this routine which are not using allocation context. So if you would like to see this logic covered here in code, you can look for init helpers 1 method inside the runtime code, which is exactly for that. It initialize the fast helpers here, making decisions based on the platform and other stuff. And do not be misled, this routine, which is used on non-Windows, is also by default using allocation context. So typically we will be using those 3 routines, we can say. If because of various reasons the object is non-typical, like it is large object heap, it should be allocated in large object heap, pinned object heap, or it has finalizers, we will use git new, the slow path. The slow path, which is just slow, and we are not super happy with it. If it is not the case, so it is a small object that will land in small object heap, we will use this on Linux or this on Windows. We can say typically it will be just those 3 routines being called. This is for an object. A very similar thing is for arrays. For example, there is a decision which routine should be called for new arrays and so on, but the logic is very similar then. So slow path is because it goes through GC, and we are not super happy with that. Fast path is super nice because it is a highly efficient routine, typically written in assembly, and it is just doing consuming allocation context in a pretty efficient way. So fast path versus slow path. Fast path will be like 99% of allocations probably, because we mostly allocate in small object heap, and occasional slow path, if they are for large objects or for objects with finalizers, we will go through the slow path. Okay, so small object heap allocation, this part, how in the end it looks. It is just using the bump pointer allocator that I've covered, and inside the current allocation context. If it is just inside it, and if it is not filling it, it is super fast, because we are just consuming the allocation context and returning from this routine. If the current allocation context has been filled, we are falling back to this slow path, which is more powerful. For example, one of the responsibilities of this slow path is the possibility to find the new allocation context if the current one is full. And as we saw, this is the one mostly often used, for example on Windows, the fast path routine. And just to show you that it is really fast, it is the code of it. So we can say that on Windows 90, obviously this is just a number as that I'm guessing, but most of the allocations in your code is happening through this routine. Alloc super fast inline get thread. And what is being done here? If you know assembly, you can read it pretty fast. If you don't, I will just try to explain it in few words. It is just doing very simple thing. So first of all, we are reading the current allocation limit and storing its value. So we are reading the current allocation limit inside the register R10. We are also reading the allocation pointer to the RAX register. Then we are adding, so we are doing this bump pointer because we are adding to the allocator pointer the size of the current allocating space. And this is because we have read the size of it at the very beginning. So in the DX register we have the size of the thing that we are trying to allocate, which is the new object that we are trying to allocate. So in the end, RDX now contains the pointer after bumping it, the allocator pointer that was seen before, plus the size that we need to allocate, and we are comparing it with our allocation limit simply. So within these few lines we are just bumping our allocator, which is super fast, few instructions, super efficient instructions. If it was inside the limit, we will just continue, and what we need is to update the allocation pointer to store it for future usage. And the only one thing that I didn't cover yet is just to store the method table, because what the allocator pointer is in .NET doing, as you see this routine, just to make it as an illustration, we had our allocation context. It is the allocator pointer, alloc pointer here, and our alloc limit here, and we are trying to create a space for an object with this size, which is in RDX register after this line. And then so we are bumping it by this size, so we are adding RDX to allocation pointer, so the allocation pointer is moved here. So now we are saying that allocation pointer is here, and that's super nice. We are comparing it with this at this line with the limit. It is inside the limit, so we are happy. We are just doing this instruction, which is now updating the allocation pointer, because we need to do that obviously for future calls. And this line is about storing method table here. So obviously we know that we have allocated this region for our object, and that's nice. We know it is pre-zeroed because we are inside allocation context. The only thing that has left is to set here a method table pointer to point it to our method table. So we need to write our method table at the beginning, and now we have an object with the by convention a header before, but it was considered like by convention. We know that there is this header before. We have stored the method table pointing to the meta table, which was passed by RCX register, and we are all done. We have just created an object with the help of those few lines, which is pretty fast, because as you see, only few instructions are allocating, and most of our allocations are happening in that way. But occasionally we will hit this allocation limit, so this will be not true, and we will need to go to the alloc field, which is just, as you see, jumping to the JIT new routine, the one which is responsible for doing more advanced stuff. So as long as we are inside our allocation context, we are allocating in a super efficient manner, and only occasionally we are falling back to this slow path. And what this slow path is doing, it is a code inside a GCCPP, or maybe not. It is a code inside somewhere in the middle between the GCCPP and other runtime elements. It is trying to do all the magic that I've described. So first of all, it tries to use existing unused space, trying to use FreeList to find a free gap big enough for a new allocation context. So this is the point, that after the very first thing that it is trying to do, it is to find a new allocation context that fits within one of the gaps maintained by the FreeList for a given generation. If it is failing to do that, so there is no gap big enough to be reused as an allocation context, we are trying to commit more memory, simply to have a more space to fit it with the new allocation context. If there is no enough committed memory, probably we have a much more reserved memory, so we will try to commit some memory from this reserved memory to have more space for it. And only if all above fails, so we were not able to reuse any space, we were not able to commit more memory, we were not able to we were not able to use already committed memory, and we were not able even to commit more memory, then we will trigger the GC. And this is the way when the most of the GCs are triggered, as you see. So we will hit the point when we are at the situation that we don't have enough space to create a new allocation context. Probably we are just running out of the committed memory inside the segment, or the fragmentation is problematic enough, we cannot reuse it anymore. Then and only then we will trigger the GC. So if you would like to have an answer when the GC is triggered, there is this answer. Most typically GC is being triggered because we have just filled our current allocation context, which means one of the threads allocating has just filled its allocation context, and we were not able to find more space for a new allocation context. So now we need to do more sophisticated things. We need to trigger the GC. And if the triggering GC will not help, we will throw out of memory exception. Sorry, that's the last resort. So here are some graphs that will be in slides that are just describing the exact logic that I was describing you previously. So we are trying to find the FreeList item, then we're trying to use one of the to adjust the limit inside the already committed memory, then try to commit more from the reserved one, and this is the logic that describes it. The logic that is trying to use that is being used by this JIT new routine. And then even more complex graph that I will not cover here because it is too complex even for this deep internal stuff, is just the logic that tries to decide what to do if we were not able to find this allocation context, and now we would like to trigger the GC. And there will be various paths here. I invite you to follow this on the slides that will be published, because we see here interesting things that sometimes the ephemeral GC will be decided to be triggered, so Gen 0 or 1, sometimes full compacting GC. It really depends on the various situations, and all this is happening when the allocation context was filled and we haven't been able to fit a new one inside the current managed heap. Various paths may happen here that tries to trigger GC good enough to find a space for a new allocation context simply. And in the end, there are some scenarios that will just say, okay, I can't allocate new allocation context, I will just start to handle out of memory exception because I don't have anything more to do. I just need to inform the process that I'm just filled with the memory. So I invite you to follow this graph as a kind of homework to see what is possible to happen when the GC is being triggered because our lack of the space. Then what we have more here, let's check the chat for a moment. Okay, it's scary, this diagram. Yes, it is. It is pretty scary, and it is scary on the diagram, and then imagine the C++ code doing all that stuff. This is really scary thing. So this was about small object heap now, and this was all about small object heap. Large object heap allocation is pretty different. and it answers the question asked before, because the large object heap, as you may remember, from various articles, is mostly for not so many big objects. And from the plan phase, you can remember that there is no plan phase. We assume that there is not so many objects there, so it is just simply using FreeList allocation. There is no concept of allocation context in large object heap. Why? Because we assume, and it was optimized, let's say, and designed for not so many concurrent allocations. If you have an application that makes a lot of large object heap allocations from various threads, it is not the scenario for which the current allocator in large object heap has been designed. Because we have the FreeListAllocator there simply, and it is using, and we don't have allocation context, so now every thread will access the FreeList item, so we need the synchronization overhead. And unfortunately also, because we don't have the allocation context concept, we need to zero memory at the time of allocation, because we don't zero memory in advance, because we don't have allocation context. So when you allocate an object in large object heap, it is just something like, let's find at that moment a free space for a new artificially created allocation context, but it is just for the purposes of similarity, but we can call it allocation context, we can call it however we would like. It is just finding a free space big enough for a given object, using the FreeList item in a synchronized manner, and then we zero this memory, because it was not been pre-zeroed, and we have this overhead of zeroing now. And because it is a big object which consists of dozens of kilobytes, this zeroing overhead is pretty big here in case of large object heap. So remember, large object heap has not been designed for many allocations, especially from various places. So we can say for various threads. So we can imagine it just as having only slow path. It is trying to find the FreeList item to find the free gap for an object. And if there is no gap big enough for it, it will try to reuse segments containing large object heap in similar manner. Again, it will try to use the allocation limit inside the already committed memory, or try to commit more memory. It may even create a new segment during the allocation because of that. So again, possibility of an overhead when you are allocating things in large object heap. That's why you should be really aware of this when using it. So answering that, there is no allocation context for every thread, because there is no allocation context in large object heap. Multiple threads trying to allocate in large object heap will just be blocked on this synchronization at the level of the FreeList item. And recently in .NET 5, as far as I remember, in .NET 5, there is this pinned object heap added, which is another another type of heap on the managed heap, which is for pinned objects. So we have this new API, which is called GC allocate array, because currently we can only allocate arrays inside pinned object heap, and we have this flag there whether we would like to have this array as pinned. And if this flag is set to true, then we are allocating in this new thing which is called pinned object heap. And one of the main feature of pinned object heap is that it will be never compacted. So by default it is pinned, objects are not moved there, so that's why we are calling it pinned. Everything there is pinned by default because we are not compacting things in pinned object heap. From the allocator perspective, there is just added a new flag when this API is being used, and then it works really similarly to the large object heap. So the same concept, free list item reusage, and so on and so on. So from this perspective, it is all again designed about not so many allocations, not so frequent allocations, because we have exactly the same overheads like in case of large object heap. They work pretty similarly from this perspective. So again, no allocation context per thread for pinned object heap with the same overheads. Okay, we should slowly ending, so just a kind of summary. A small object heap is super fast bump pointer allocator inside allocation context, so it is super nice. It is 99% of the time working efficiently at the level of only these few assembly lines that you have seen. And sometimes, from time to time, when the allocation context is being filled, we are falling back to try to reuse the free list to find a new place for an allocation context, or maybe use a already committed memory at the end, or maybe commit more memory from the reserved memory. Then we need to zero this memory, unfortunately, but this happens like every few kilobytes of allocations, depending on the current allocation quantum. And large object heap and pinned object heap are the overhead here is mostly dominated still by the zeroing cost, especially for large object heap, where we have big things being allocated with additional overheads like the additional synchronization. And as you may remember, during the concurrent sweep phase, there is a part of the concurrent sweep when the large object heap allocations are blocked and paused, because concurrent sweep operating on large object heap is operating on the free list item. So at the time the allocations are not allowed, so they can be postponed because of the ongoing concurrent sweep, which again, I covered that even previously, may be reported because there is an event for that, and you can see it in purview that you have large object heap allocation pauses because of the background GCs, because of that. And the stack alloc, which is not covered, like using stack is a totally different story. It is not touching the GC, so you can use value objects like structs or stack alloc directly to allocate things on the stack, and they will also mostly have the overhead of zeroing the memory, because we need to zero part of the stack frame, which may be disabled with the API recently added, but this is not the story we are covering today, because it is not about the GC, it is about using the stack. Okay, so time to prepare questions from your side, because this is again one similar time, like 1 hour and a half. So if you have any questions, now it is a perfect time to ask them. And covering the code, if you would like to follow the code in the GCCPP, yeah, that's funny name. Allocate object is the routine that you can start from, and it is calling GC heap alloc, and it takes various flags, like for example the runtime, obviously based on the metadata, will report that, for example, this allocation is about object that has finalizer, or it is a large object, or it is an object that should be in pinned object heap. So this alloc will, depending on those flags, call allocate UOH object, which is umbrella term for large object heap and pinned object heap. It is called user old heap for both of those heaps. So the allocate UOH, I don't know how to spell it in English, sorry, object is used for a large object heap and pinned object heap, and for small object heap there is just GC heap allocate, which is doing all this magic. And then you can find more things like allocate more space or try allocate more space. this is the code used by these magic internals to try to fit the new allocation context based on all those FreeList items and so on. So those are the methods that you can start to investigate if you would like to follow how they are really implemented. But I hope that this 1.5 hour explains it in a complex enough way that describes and covers how it is working, at least at some level of complexity. Okay, time for questions. The question number the first question, it will be used for root objects. I don't know what it will be used. Sorry, I don't know the context. So if you could say again what we were talking about at the moment. So I will move to the next question. Considering the .NET 5, except manually triggering a large object heap compaction, can also GC decide to compact the large object heap itself on the planning phase? Yes, I mean, it was recently added for the very first time in the history of the .NET runtime. In the container scenario, when there is a hard limit of the heap, you can set a hard limit that you don't want to use more than a given amount of bytes, and it will be generally called the containerized scenario. The GC may decide to compact large object heap automatically. The very first exception from this rule that you need to manually trigger the compaction of it. It may be triggered automatically, mostly because we are in the scenario in the containers, so we expect the heap is not big, and we would really be really aggressive in reusing memory and fight with fragmentation at maximum. So compacting large object heap here is more beneficial, even with overhead of doing it, instead of not compacting and being hit by out of memory exception because of, for example, fragmentation doesn't allow us to allocate something in large object heap. So yes, in this container scenarios, the compaction may be automatic. Then what about objects bigger than an allocation context? For example, yes, then we will find a new allocation context big enough, like create a new one. Sorry for that. So bigger than allocation context, smaller than the large object heap threshold. It will be just created in a new allocation context. That's a pretty good question, because I don't remember now whether it means that we will discard the current one and just start to use the new one. Probably not, because it wouldn't make any sense to discard the current one. What is the exact path of handling it? I need to check, because I would expect that it will be just created kind of on the side, trying to find a new allocation context, kind of artificial allocation context for this big object, while still using the old one, but I need to check. Or you can check yourself and give me a update on Twitter, for example. The source code is on GitHub. Pinned object heap will be used for root objects. In general, pinned object heap is something that you need to use manually. So as far as I remember, currently there is no code that is just allocating something there automatically. Every time when you new up something, so every time you create new object by using new keyword, it is either in small object heap or large object heap. The only way to allocate something in pinned object heap is to use this, and the only one, in fact, API, which is called GC allocate array, which allows you to manually say that I want to create an array that is by default pinned with a given size, and if you set this flag to true, it will be pinned because it will be allocated there. There is one limitation again, currently, although it could be different way, currently this array cannot contain references, and in general the current implementation of pinned object heap is something that doesn't handle objects that contain references. So you cannot allocate references or objects that contain references inside pinned object heap. And this is a design decision, like we could do that, it could be handled, but because current idea of pinned object heap is to have a place for buffers, probably, that are passed to unmanaged code, which probably means indeed we are mostly interested in allocating arrays of primitive data like bytes or ints, then only this kind of objects may be allocated there, and the runtime will throw an exception if you try to allocate an array of strings, for example, there. Unfortunately, it will be handled at runtime with the exception that, sorry, you cannot allocate array of strings there because they contain because they are references. Why is that? Because the pinned object heap may be treated differently. If we know that it doesn't contain any references, we can omit the whole pinned object heap during the mark phase, because we know by this API limitation that there are no references on pinned object heap, so we don't care about objects there in terms of the mark phase, and in general in tracking outgoing references. We don't care about the intergenerational references from there because there are no references, and so on and so on. So it simplifies the API and reduces some overhead while providing some limitation. I hope it answers your question. Okay, so it is a perfect time, 90 minutes. Like previously, almost ideally. So if you don't have any questions, I will be slowly ending. See you next time when I will be covering the generations and the overall physical representation of it, because we currently know pretty a lot. Like we know all the algorithms used by the GC, sweeping, compacting, we know how the planning is being done, we know how the GC cooperates with allocators, with all these FreeList items. Then we know the allocation context thing, and now we could even end the whole story, because now this could be implemented in that way, but it would be inefficient because we would need to treat the whole managed heap as a whole. And to make it more efficient, we introduce the generation concept, so we split the whole managed heap inside the smaller parts called generations, and all the stuff that I've described so far is based and reusing all this stuff is reused to fit within the generation concept, which will be covered next week. So thank you very much. I'm super happy the internet was good enough, at least I hope so, because it was a new place when I was not sure how the internet will be behaving, but it seems it is good enough. So thank you for being today with me. See you next week. If you like this video, I forgot, and I'm always forgetting that. If you like this video, plus you can subscribe me or just give a like under the video, because it just improves the visibility of the video. It is not about me being proud of doing something, but I would really like to reach as much people as possible with this. So subscribe, add a like, and see you next time. Bye.